right, warm up. So find two non-zero vectors orthogonal to -3, 5, -2. I know you hear orthogonal now and you think cross product because the cross product produces a third vector that is orthogonal to two other given vectors, right? But you don't have two other given vectors, you just have one. Now, because there's just one, there's infinitely many vectors orthogonal to it, right? You have any, like in any direction, like all of these are all orthogonal to this one. So, and it's actually a dot product question. So I don't know if you remember this or not, but if you have two vectors and you find the dot product and the dot product is 0, then the vectors are orthogonal, right? So, bless you. So there were a million answers, like as long as, so you just needed to pick numbers so that when you added these together, bless you. So I picked 1, 1, 1, so I get -3 + 5 + -2 = 0, right? And then -1, -1, -1, so you get 3 - 5 + 2, right? But there's infinitely many. Like there's 1, 1, 1, and 2, 2, 2. That works also, right? Well done. So lots of different answers. So on this board we have 5, 3, 0, -15 + 15 + 0 is 0. Beautiful, right? Okay, so tons of different answers. Ooh. 1, -7, -19. Let's see. Okay, so -3 - 35 is -38 + 38 is 0. Wow. All right. So yeah, very good. You found one or two. Yeah. Okay, good. Yeah, all different answers. I'm assuming they're all correct. I don't know. I'm not going to try every single one, but it looks like most of you got the idea. Yes, Sophie.
So is 0, 0, 0 just orthogonal to like every single vector ever?
0, 0, 0 is just a dot.
Okay.
Right. So technically, can a dot really be orthogonal to anything? I mean, that's more a philosophical question, right? So I mean, it's not a vector. It doesn't have any dimension at all. I guess it has a magnitude of 0, so I guess you could say yes, but you could make an argument for no.
Because the dot product would be 0.
The dot product would be 0. So, except there isn't an angle. Like it's hard because normally the dot product is 0 because of that angle, but now if there's no angle, I don't know. I'd have to think about it. I'd probably have to just look it up and see. It's probably just defined somehow. And I'd have to look and see what the math world has decided that answer is. But speaking of you asking deep philosophical questions, I have found answers to all of your other questions.
Hey.
So I added them into my Smartboard notes for the cross product lesson for next semester. So next semester they'll get all those answers without even asking the questions because I figured them all out. So some I looked up, some I figured out. But it was good. It was a good exercise for me to figure it out. All right, so for number 2, a 20,000-pound truck sits on a 5-degree, let's say inclined slope. Assuming no friction, what is the force necessary to keep the truck from rolling down the hill? So for this one, there it is. Okay, I personally just set up a triangle and used a trig. So that was me. So I kind of cheated, but anyway. So I did draw a little bit with vectors. So the weight of the truck, I consider that to be this vector pointing straight down with a magnitude of 20,000. So that weight, I'm considering the force going in the vertical direction, right? Then, okay, we had this long argument last year about which way the arrow should be pointing for this vector. I don't want to get into it, right? So anyway, you have like this little incline, right? That's 5 degrees. So I just went this way only because it was easier for me to make a right triangle going this way. So, right? So I know then that this angle is also 5 degrees because it's vertical to that one. I kind of covered it up. So that's 5 degrees. Okay. And then we have this cute little right triangle, right? So what have we got? Well, let's see. There's different ways, like do this way, this way. How did I get, let's see. This is 20,000. This is 5, which means this is 85, which means this is also 5 over here. Okay, so then that means that this guy is 20,000 sine 5, this guy is 20,000 cosine 5, and I just did it with trig. So your answer would be this component right here, this guy, that vector. So 20,000 sine 5. I just did it with trig. Yes, Tejas.
Okay, why is it 5 degrees again? Like,
So, sorry, my markers are fat. If this angle is 5, right, and this is vertical, this is 85, right? So this, here, I'll write it like this. So this is 5.
wait, that's the angle that's 5? I thought isn't it supposed to be the angle like where the incline starts?
This is 5.
Yeah.
Therefore, this is 5 vertical angles.
Oh, right, I didn't see that.
Right? Therefore, this is 85. Therefore, this is 5. Yep. Yeah, that was my approach at this problem. Okay. Okay. This one, this one wasn't so bad. So for me, so you have, whenever I've got, am I pulling something along the ground? What do we do? An object is pulled 20 feet across the floor with a force of 112 pounds in a direction of 50 degrees. Find the work done. All right, so this one, you've got an object. It's pulled this way, 20 feet. It's being pulled by some vector this way. What was the angle? 112, 50? Oh, 50. 50. This is 112. We want the work done, right? So your work is the dot product of your force vector and your motion vector, right? So our force vector, you can either, did anyone like come up with the projection and do all the work with that? Or did you guys just do simple dot product, right, the force vector? Or did you do something else? Okay, so I just found, so my force vector is 100, writing it in component form, right? So this guy right here. So since that's 50, my horizontal component is 112 cosine 50. My vertical component is 112 sine 50. That's my force vector. My what did I call? Oh, there. My distance vector, I should call it my motion vector. My motion vector is 20 this way and nothing up or down. So it's just 20, 0. And then I just did their dot product. And remember, work is just the dot product of the motion. I should probably call it motion. Okay, have fun. Motion vector and the force vector. So you got it. You got it. You got it. No. 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 We're like 50-50. Okay. So let's just review. This one, I will tell you the truck problem, don't worry about so much. I really need to just take that off. But this one's a good one. This one's just a nice normal work equals the dot product of the two vectors. So your work is just the dot product of your force vector and your motion vector. You just need to write them in component form. All right, so let's get into today. Today we're learning how to find the equation of a plane. Yesterday we did equations of lines. Today we're doing equations of planes. I am going to need a whiteboard. And some dowels. I am ready with my visual aids. Here we go. All right, so today we're going to figure out how to write a linear equation to represent a plane in space and find the angle between planes in space. It seems weird to have a linear equation to represent a plane. It just means that all the variables are first degree. All right. So 12.5b. Everyone have 12.5b written down? Planes in space. Ryan, you ready? Are ya? How you doing today? Yeah? It's kind of a cold, rainy day. Did you have to walk in the rain this morning?
I walked a lot.
From which lot?
A lot.
Is A lot close? Okay. So is C lot the far one?
Yeah.
How many had to walk from C lot?
No.
One, Ahad? All right. So one student. All right. Did you get wet?
Yeah.
Yeah. Okay. So, yesterday we learned how to write the equation of a line given a point and a direction vector, right? So today we're going to learn how to write the equation of a plane using a point on the plane and a vector normal to the plane. The reason we can't just use a point and a vector on the plane is if I have a vector on the plane, are you going also to the, is someone going to that college visit? Yeah. Okay. Okay. Well, fun. See you in a half hour. I don't know. Okay. All right. So anyway, if I have a vector on the plane, there's infinitely many planes that pass through one vector, right? So it doesn't help me. So instead, if I need a plane, well, two vectors actually technically produce a plane, right? If I have two vectors, then I have a plane that passes through the two vectors. But the way that we do equations of planes, so that we can write it just as a simple equation without having two vectors in there, is instead, if we have a point on the plane and a vector normal to the plane, now there's just one plane where that's true. Because if you think about it, we've got a point, this vector is orthogonal to this plane. That's it. It's just this plane. There's no other planes that pass through that point and have this orthogonal to them. So when we write an equation of a plane, like a line, you use a vector along the line, right? Direction vector of the line. Planes are opposite. Planes, you have a point and use a vector that's not on the plane. Use a vector orthogonal to the plane. All right, so that's what they're calling n here. So if P is a point on the plane and n is a vector perpendicular to the plane, then the plane consists of all vectors through P that are orthogonal to n. So it's weird to think of a plane as a set of vectors, but it is. It's kind of like saying a circle is a set of points. Have you guys ever heard definition of a circle of the set of all points equidistant from the center, right? And you just put them all together. It's the same thing here. So you've got a point, you have a vector. The plane is the set of all vectors through that point orthogonal to this vector, right? So anyway, okay. All right, so if Q is any other point on the plane, then n dot PQ, so if Q is a point on the plane, you get this vector PQ, that means these two vectors would have to have a dot product of 0 because they'd have to be orthogonal. So if you let vector n, be ABC, and vector Q, or PQ, Q, oh, they're doing it like this. Okay, and point Q be XYZ and P be X1, Y1, Z1. So this is the point that we've identified, and Q is like any other point on the plane. So they're not giving Q subscripts, they're just saying a generic XYZ. Then we get ABC dot X minus X1, Y minus Y1, Z minus Z1 equals 0. So it's actually a pretty simple process to come up with the equation of a plane. This is it right here. It's just the dot product of n and vector PQ. And you're just saying, hey, that dot product is 0. That thing right there is how we write the equation of a plane. So you'll get used to, you probably won't think of it too often as n dot PQ, but what you'll get used to is this right here, that's your normal vector. And then this right here, that's a point on the plane. So for a line, you need a point and a direction vector on the line. For a plane, you need a point and a vector orthogonal to the plane.
So ABC is the vector.
That's your normal vector.
That's your-
Yes. But do you guys know normal means perpendicular?
Yeah.
Okay. So when we say the normal vector, we mean the vector that's perpendicular to the plane. That's what they use n. They use n a lot for normal.
So normal, you can substitute with one.
Yeah. Yep. You could substitute perpendicular. Yeah. A lot of different words with very similar meanings. All right. So the reason that general form tends to be nice is that general form tends to be simplified. So like this one, you can have this ugly thing with like really big, nasty numbers. And then when you multiply it out, it actually simplifies kind of nicely. And it's easier for me to grade if it's in general form. But I will usually accept either way. So anyway. All right, so we're going to start by finding the equation of the plane that contains these 3 points. So, I didn't give you any vectors at all. Okay. So, should I give you any hints on how to start, or do you guys want to figure it out completely?
Yeah.
You want to figure it out?
You want to figure it out?
Yes, please.
Okay.
Wait, what's the D in general form?
So, there's going to, when you multiply all this out, you're going to end up with a constant, right? You're going to have some number times x plus some number times y plus some number times z plus whatever ax1, by1, cy1, z1 lumped together to b, and you just call that constant d. Does that make sense?
So we have to set up the same form.
Yeah. Absolutely. Yeah. All right, I'm giving you a minute of silent mulling. Mull this over individually. After you've mulled, then you talk to each other for another minute, okay? All right, so take a minute to mull. That's it. So in order to find the equation of a plane that contains these points, so in the warm-up, don't confuse this with the warm-up. The warm-up, all we found was a vector orthogonal to another vector. When you're going vector orthogonal to another vector, there's infinitely many of them, right? We can't use infinitely many. It can't be a random, just, some random vector. It's got to be a vector that's perpendicular to that plane. So I can't do a random dot product. So what am I going to have to do instead? I'm going to need 2 vectors on the plane so that I can do cross product and get that perpendicular vector. So how do I find 2 vectors on the plane? Tejesh, how do I find 2 vectors on the plane?
Terminal point minus the initial point.
Exactly. I subtract any 2 points. Dorsa, does it matter which points I pick? No. Does it matter which order I pick the points?
No.
Not at all. As long as you get 2 vectors on the plane, right? So, blah, 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 blah. So I did this. It looks like I did this minus this, this minus this, and then I did this minus this. I did second minus first and last minus first, right? But you could have done last minus second, right? Or second minus last, right? It doesn't matter, right? But you just need 2 vectors, non-parallel, 2 vectors, 2 different vectors on the plane. All right, so then I did a cross product. Back then, I was still doing diagonals. Ignore that. You should have done expansion by minors. Either way, you get 9, 6, 12. So the equation of the plane. So you can pick any point as long as where's the point? As long as it's a point on the plane, right? It looks like I used the first point. So this is standard form equals 0. By the way, if there's no equals 0, it's not an equation, right? The equation has an equal sign. Okay, so standard form, or you could distribute out and get general form, or you could reduce it. Or, let me ask, well, or, I've already discussed this, I think, with every group, but suppose instead of using this, I let my normal vector be 3, 2, 4 right at the beginning. Would that be okay?
Yeah.
Ian?
Yes.
Oh, yeah, pretty much when I was baseline and then it's just going through.
Yeah, very good. Okay, so the reason you can reduce, which will come in handy when we get into application problems, the reason you can reduce is because we're not using this vector for its magnitude at all. We're just using it for its direction. So you can have any scalar multiple of the orthogonal vector and it'll still work. Okay, so if you got, like some of you got all negatives, that's okay, right? It's just a scalar multiple. All right. Okay, so let's do another one. Find the equation of the plane that passes through the point 1, 2, 3 and is parallel to the YZ plane. Dun, dun. So you're going to need to come up with a vector orthogonal to the plane. So think about it for a minute. And I showed you in the solution, or I showed you the math behind it, but we're going to talk about this in a minute. So a vector normal to the YZ plane is the x-axis, right? So because the x-axis is normal to the YZ plane, you could just use 1, 0, 0, right? You could use 20, 0, 0. As long as you're perpendicular to the YZ plane, then when you set up your equation, you get whatever this is. Could be 20, could be 1, could be 152. It doesn't matter because when you clean it up, no matter what you get, like no matter what you put in here, you're going to end up with x equals 1. So at x equals 1, so that's an equation of a plane. We knew that because we talked about that like on our very first day. So our very first lesson, we talked about x equals 1 representing an equation of a plane. And it's the equation. So right here, I'm sitting on x equals 1. Doesn't matter what the y or z are. Every single y and z, as long as the x is 1, is on this plane. Just think of it going out in all directions for every y and z to infinity. As long as the x is 1, it's on this plane. Does that make sense? Yes, Dan. Then you'd be on this plane, and you wouldn't pass through the given point, right? So you have to be on x equals 1 to match the criteria of the question. Yes, Lily.
So if so if the point was something like 2, 3, 1 instead, would your vector be 2, 0, 0 then?
The vector has nothing to do with the point. The vector is, all you need for a vector is a vector that's orthogonal to the YZ plane. So I picked the x-axis. The x-axis, anything on the x, any vector on the x-axis, you can pick any x value you want. Like even for this problem, instead of picking 1, 0, 0, suppose I picked 20, 0, 0. I'm still on the x-axis, right? So it's just a different magnitude, but it's still the same direction. So here, instead of 1, if I had 20, what would happen? Well, this is gone because those are all 0, and I got 20x minus 20 equals 0, which gives you x equals 1. You're going to get x equals 1 no matter what.
So the point is.
Well, the point does, because
Well, I mean,
that was what was here, right? You need to chew for a minute? I'm seeing some faces.
I get it, but I don't get it.
The magnitude of your direction vector doesn't matter. Your direction vector, you can use any scalar multiple of the direction vector that you want.
That makes sense. YZ.
The y, okay, do you know, here. This is the YZ plane. You need a vector perpendicular to the YZ plane. All right? So when anything that's going to come out this way, right? Now remember, vectors don't have location. So okay. So no matter what, if I'm sitting over here, I'm still the vector 1, 0, 0. Why am I still the vector 1, 0, or 100, 0, 0? Some x value 0, 0. The reason I'm some x value 0, 0 is if you pick 2 points on this vector, when you subtract their x's, you will get a number, but when you subtract the y's, you'll get a 0, and when you subtract the z's, you'll get a 0. Because there's no change in y and there's no change in z. There's only change in x. So no matter where I am, I'm gonna, like, it doesn't matter where the vector is. So I pick the x-axis, right? But technically, remember, vectors don't have a location, right? So they just have a direction and a magnitude. For orthogonal vectors to a plane, when you're writing the equation of a plane, the magnitude makes no difference, just the direction. So I could have actually done -10, 0, 0, and I'd still be fine, right? So your direction, as long as it's a vector orthogonal to the YZ plane. All right. So that's what gives you the, okay. The orthogonal gives you the plane, like the direction, the orientation of the plane, but then the plane has a location, like it's got to have a spot. So this plane, it's the point that now takes this and puts it here, right? The direction vector is what makes it go this way as opposed to, like, you know, that way or something, right? So the direction vector makes it go this way, and then the point is what sticks it in that spot. Okay. Yeah, Sophie.
So we didn't think of like the x-axis thing, but we were doing like we did the 3 points like 1, 2, 2, 1, 1, 1, 1, 2, 3, and we were just gonna find vectors off of that.
That's fine.
Too.
You'd still generate a scalar multiple of the x-axis. Yes, okay. Absolutely. That would work just fine. So did you guys hear that as an idea? So they said, hey, why don't we just pick 3 vectors or 3 points that, did you pick 3 points that you knew would be on the plane?
Yeah, because the plane is just the one.
Yeah.
So
you knew it was x equals 1.
Yeah.
But then you just went ahead and did a whole bunch of work to prove it was x equals 1. Okay.
Yeah.
All right. That's good. All right. Okay.
We were right.
Okay.
Yeah, we were just waiting to proof, I guess.
Yes. Okay. All right. Dun, dun, dun. Find the equation of the plane that passes through those 2 points. You have 2 points on the plane. I think you know what you're going to do with those. And is perpendicular to the plane. Perpendicular to the plane 6x plus 7y plus 2z equals 10. You think you had to use your brains for the last 2? You're going to have to push them up a little bit. Okay? So, have some good discussion. Had some fun with lots of visuals. So here we go with some visuals. You have, let's just pretend, I'm going to set this thing down. Okay, I'm going to go through what I just walked through with a couple of groups. So let's pretend this is the plane we want. All right? Are you all okay with that? Okay. Now, thank you. I'm going to take this too. All right. Oh, and I'm going to take one more. The 2 points on the plane produce some vector on the plane, right? Okay. Everyone's okay with that, right? Now we have another plane that is perpendicular to the to this plane, right? So perpendicular. The vector that is identified in the equation of this plane is perpendicular to its own plane. Bam. All right? Now, vectors don't have a location. They just have a direction, right? So these two technically are coplanar. They're both on our plane. Okay? Right? If this is perpendicular to this plane and this plane is perpendicular to our plane, then this is parallel to our plane. Perpendicular to perpendicular means parallel. Right? Okay. So now we have two vectors essentially on the plane, and so we do the cross product to generate the vector normal to the plane that gives us the equation of the plane. So, vector on our plane, vector normal to the plane, cross product, -4, or I got 40, -36, 6. Again, you could simplify before you write it, right, down to 20, -18, 3. So either way, so this or this with these reduced, or this, they're all correct. Or a negative times all of them. Or any scalar multiple, right? If you want to go bigger and make it, 80, -70, 212, right? You can. Please don't, right? Because then I got to make all these answer sheets. You should see my answer keys for your tests. Well, if they do this, then they do this, and if they do this, then they do that. It's so crazy with some of these problems. Anyway. All right, good. Last little note here is the angle between two planes. You know what? I'm going to keep these for a minute. All right, stay with me here. Tejesh,
Yes.
do you need time to write?
Yes, please.
Okay. Can I have someone who doesn't need a lot of time to write up to help me with a demo? Okay. Dorsa, will you come up here, please? Okay. Hold. Please. Dorsa. Am I saying it right?
We're just ignorant.
Okay. All right. Good. All right. So will you hold this here too, please? You got them?
Yeah.
All right, guys. We want the angle between these two planes, right? So there's no formula for an angle between two planes, but we have a formula for an angle between two vectors. Now, if I have the vector normal to this plane, I don't want to hit you in the face. I'm going to do it like this. And the vector normal to this plane, right? Then the angle between these two vectors this way is the same as the angle between these two planes this way, right? And the complement would just, would be fine. So when we thank you. Okay. So you guys didn't get a good, sight line. Okay. So if we need the angle between two planes, it's the same as the angle between their two normal vectors. All right? Every pair of planes has two angles, technically. It has acute and it has obtuse, right? So you take two planes, you put them together like this, you got a little angle and you got a big angle, right? Right? Unless they're perpendicular. So anyway, when you do the two normal vectors, same thing. You're going to get an acute angle, you're going to get an obtuse angle. They're going to match the angles between the two planes. Yes?
That's an absolute value, right?
And one dot n2.
Why do I have... Oh, you know what? This is just to get the acute angle. Yeah. So if you kept the absolute value off, yes, thank you. If you kept the absolute value off, then you'd get possibly the obtuse angle. It just depends on how they go. So yeah. I think your WebAssign wants the acute angle every time. I was reading through your book and I'm pretty sure they wanted the acute angle. So I think that's why, and I think even the last book did too, because I haven't changed this, so that's an absolute value. Because whenever you do an absolute value, that inverse cosine is going to be acute. All right. By the way, if two planes are parallel, then their normal vectors will be the same or scalar multiples of each other. Note. If two planes are perpendicular, then their dot products, the dot product of their normal vectors will be 0. All right. Oh, sorry. Going back. You're welcome. So we're gonna do another parallel, orthogonal, or neither page, but this time with equations of planes. Boy, those of you who are out, you guys missed some fun.
If we do listen to the recording.
Oh, it's time for core. Okay. No, we're not gonna just keep going because core time is your time. So, right? Okay. So anyway, I think you can do this though, right? You pull out the normal. What's the normal vector for this one? 3, 1, -4, -9, -3, 12. Right? If they're scalar multiples of each other, which I think they are, then the planes are parallel. Right?
They are.
Okay. If you pull them out, you do a dot product, and you get 0, then they're perpendicular. If they're neither, then it's neither. Right? That's all it is to parallel perpendicular. Then we just had some review, which we're not going to do. Okay. So for core, let me pause this.